This is the third lecture in the power semiconductor types. In this lecture, we are going to discuss about what is the fundamental torque equation and what are the different load torques. Suppose if any motor which is driving a load, in this case we have taken the one motor which is driving the conveyor belt. See, this is the drum which is connected to the shaft of the motor. This is a belt. On the conveyor belt, we have kept some load. Total thing is acting as a load. So when the motor is rotating, this belt also will be moving linearly so that this load will be passing from the one place to the another place. Nothing but this load is giving a load torque which is opposing the torque which is generating in a motor. Now the same thing if you represent it in a block diagram. This is the motor, this is the direction of the torque, this is load which is applying opposite torque to the generated torque. This is the speed of the omega m is nothing but the speed of a motor. Now this is one more example where the motor is driving a wheel. Now we are predefining the some of the terminology what we are going to use in a fundamental torque equation. J is nothing but a amount of inertia of both motor as well as the load in a kg meter scale. Omega m is nothing but a instantaneous angular velocity of the motor shaft in radians per second. T is nothing but the torque developed, nothing but a generated torque in a motor in Newton meter. TL is nothing but a instantaneous load torque which is referred to the shaft of the motor in Newton meter. This is the fundamental equation which is representing the motor as well as the load. This is the generated torque, this is the load torque. The difference between the generated torque and load torque is equal to the d by dt of j omega m. J is nothing but a moment of inertia, where omega m is nothing but the speed of a motor. Now, if you differentiate this one, the J is nothing but a constant. So, you apply the UV formula in a differentiation. J into d by dt of omega m plus omega m into dg by dt. This is a constant. So, the differentiation of constant is 0. Now, the total quantity becomes 0. Now, this same equation we can write it as a. Now we have taken the minus TL that side. So T equal to TL plus J d omega m by dt. This is nothing but a dynamic torque. This torque is presented in the motor only when the transients are occurs in a motor. Nothing but at the time of starting, whenever you apply the load on the motor, and moreover, speed reversals and braking of the system. During the transient operation only, this term is coming to the picture. This is becomes a zero once the motor is going to the steady state speed. Because when the speed of the motor is constant, the derivative of the speed becomes a zero. So this is constant. When the speed of the motor is changing during a transient period, nothing but the starting period, nothing but when we are applying braking, when you are increasing the speed of motor, when you are reversing the motor, by the time only this term will be coming to the picture. So this is called it as a dynamic torque, which is present in a transient operation. Now here one more term is there. This is the try to understand here this equation. The total torque which is generated in motor that should be equal to the load torque and dynamic torque. Now we are going to see the what are the different types of the load torque. This load torque T suffix small l. It is also taken into consideration of the windage and friction torque also. Now the components of the load torque. There are three components of the load torque. One is friction torque, windage torque, and torque required to do the mechanical work. Friction torque. When the motor is rotating, there is some amount of friction will be occurs in the motor as well as the load also. So due to that, which is opposing the speed, so that we are calling as a friction torque. The friction torque has three components. One is static torque. Nothing but this torque is experiencing in the motor at the time of starting. Nothing but when the speed of the motor is zero. When the speed of the motor is increases, this torque is becomes a. Next one more torque is proportional to the speed. that we denoted with a T suffix V, that is equal to B into omega. So to remove that proportionality, we are keeping one constant. This is the one term which is representing the torque is proportional to the speed. So one more thing is that the torque which does not depending upon speed, nothing but a Coulomb torque, that we denoted by the TC. These are the three components of a friction torque. Now here we are going to see the what are the different components of a friction torque. This is the static torque, nothing but when the speed is zero, the torque is very high. When the speed is increases, the torque will be. This is nothing but a torque which is proportional to the speed. This is nothing but a Coulomb torque. Now sum of the three is nothing but a friction torque. We are getting the resultant graph. This is representing the positive direction of the speed. This is representing the negative direction of the speed. The positive direction means we are assuming that the motor will be rotating in one direction. Suppose if the motor is running in opposite direction, that is nothing but a negative speed. Next, wind is torque. When the motor is rotating, the wind is offering a some amount of opposition to the speed of the motor, that we are calling as a wind torque, that we represent it as a T suffix W. It is always proportional to the square of the speed. So to remove that proportionality constant, we are keeping one constant. So T suffix W equal to C into omega m square. Next, third component is the torque required to do the mechanical work. This is the important component in a load torque. This torque is depending on the nature of the load. Sometimes it is independent of the speed, motor speed. In some cases, it will be depending upon the motor speed. It is also depending on the position, how the load is following the path. Suppose if you take the traction load, if you take the train, electric train, when the electric train is going into the heights, then torque opposing on the motor will be different. When the electric train is moving downwards of the, then the torque which is applying on the motor will be different. Next, time invariant. Sometimes this torque also may not be depending upon the time. In some case, in some situations of the load, the torque is time variant. It follows cyclically, and its nature will be depending on the load's mode of operation also. Now this is the equation for the load torque. The load torque equal to TL is nothing but the torque required to do the mechanical work. This is the linear torque, this is the Coulomb torque, this is the windage torque. Generally, in any drive, these two components will be very low when compared to this one, linear torque. So we can neglect this one. If we neglect that component, then we have a equation low torque equal to the torque required to do the mechanical work plus linear torque. The torque which is proportional to the speed. Now we know that this is the equation which is relating the low torque as well as the torque which is developed in a motor. This is the torque which is developed in a motor. This is the low torque. This is the dynamic torque. This torque is presenting in the motor only when the motor is going to the transient operation. Now in place of low torque, now we have to substitute this one. Now we are getting the final equation. This is the equation which is representing the motor along with the load. So the generated torque equal to the dynamic torque plus the torque which is required to do the mechanical work. This is the linear torque which is depending upon the speed of the motor. This is the final fundamental equation for any drive. Now we are going to see the nature and classification of the load torque. How this load torque will be depend. Suppose if we take the low speed hoist, this hoist is driven by the low speed motor. So whenever the speed of the motor is low, windage loss will be neglected. So the torque which is applied on the motor is only the gravitational force. The net torque is depending upon the gravitational force which is constant. We might have seen the fans, compressors, and aeroplanes, and centrifugal pumps, ship propeller. In some loads, air is opposing the speed of the motion. In some loads, some fluid is opposing the flow of motion. Nothing but in case of compressors and centrifugal pumps and ship propeller, in three cases, water is opposing the speed. Fans and aeroplanes, air is opposing the motion of the motor. So in all these cases, the load torque is directly proportional to the square of the speed. So if we represent the graph between the load torque, speed and the torque, this is the profile of the graph. It is representing the parabola. In high speed hoist, the high speed hoist, viscous friction and windage friction has appreciable amount compared to the gravitational torque. Thus, the speed torque characteristics are shown in the figure. This is the profile of the load torque. The load torque characteristics are nothing but it is a curve drawn between the torque to the speed. So this is the figure in which we can observe the high speed hoist. So this is the motor. Here we can see the high rate of the motor, so that this is a hook by which you can hold the some load. High speed hoist means fastly drop this hook to the ground, as well as fastly you can move upwards also. So by the time the speed, the windage and fractional loss also will be more when compared to the gravitational torque. So this, if you observe this graph, when speed is zero, this is the region. When speed is zero, there is some amount of torque is present. Torque on a traction load. At the time of starting, the static torque is more due to the heavy mass of the load. Suppose if the train is starting from the one station, the mass of the total train is very high. To at the same time, at the time of starting, to move that high mass body, high amount of static torque is there. Once the speed of the motor is increases, then the torque required to move the vehicle will be lesser. Once the speed is increases, the windage and viscous friction dominates, where the static torque will be disappears. This is the profile of the graph between the speed and the torque for the traction load. Torque in a coil driver. In some cases, this is the coil driver. We are driving the coil. In this case also, the motor is required. See, the speed torque characteristics of coil driver is a rectangular hyperbola. The power taken by the motor will be the constant. When the speed is very higher, it requires a less amount of torque. Speed is lesser, it requires high amount of torque. But this drive is taking the constant power from the supply. So sometimes we are calling this drive as a constant power drive also. We're going to summarize this class. In this class, we have discussed about what is the fundamental equation for the torque in any electric drive. Next, we have seen the what are the different components of the friction torque. Next, we have seen the windage torque. We have discussed about the what are the different load torques are available practically. In load torques, we have observed the low speed hoist and high speed hoist and the traction and fans, compressors and propellers. Coil driver, finally we have observed the coil driver. The power taken by the coil driver is a constant. So we are calling this drive as a constant power drive also. Thank you very much. If you have any doubt, you can ask in the comment box of my YouTube channel. I am available to answer all your questions.